Now let's talk about the internet. As we mentioned at the beginning of this workshop, the internet is filled with autonomous systems. Here we have an example of two autonomous systems. On the left side, AS701 is the Verizon autonomous system, which our PDU is currently traveling in. And on the right side is AS32934, which is Facebook's autonomous system, which is connected to the web server we're trying to request website data from. Inside the Verizon autonomous system, our PDU is hopping from router to router using the OSPF routing protocol. OSPF stands for Open Shortest Path First. This protocol creates a map of all the different devices and connections in the network. Then it calculates the shortest path between the devices using a special algorithm. That way, when you send data from one device to another, it can take the shortest path and most efficient path possible. In between autonomous systems is the routing protocol known as External Border Gateway Protocol, or EBGP. EBGP uses peering to establish a direct connection between two networks so that each BGP can be used to route data between them. Our PDU reaches Facebook's autonomous system. It'll use OSPF to travel the routers of Facebook's AS autonomous system. And when we mention hops, we only count the routers, so the modem and switch would not increase the count of hops. The final hop would be the actual destination, which in this case is the web server. Let's take a closer look at OSPF. OSPF breaks down an autonomous system into areas. We're going to take a look at the OSPF neighbor table and the Cisco Discovery neighbor table of one of the routers using OSPF to dive a bit deeper. Up here is the OSPF neighbor table, and down here is the CDP table. CDP standing for Cisco Discovery Protocol. So these router IDs are manually assigned to each router used when configuring the OSPF settings. So in this case, 1.1.1 is for router 01 down here, 3.3.3.3 is for router 3, and 2.2.2.2 is for router 2. We are on 4.4.4 as we are router 4. So that's just manually assigned. You could assign it anything, but this makes it easier for you to keep track of things. So the full state here, this means that the router's link state OSPF database is complete. So we received and processed all the other router links being advertised to us using OSPF. So full is good because that means its database is up to date and complete. DR stands for designated router, which means that this router here is the central point. This router right here is the central point, 1.1.1.1, is the central point of communication for these other routers, including us. So the DR router will exchange the routing updates with the other routers for this subnet of the network. So we can see that the designated router is connected to this router's interface gigabit Ethernet 0/0, or G00 for short. So BDRs are the backup designated routers for these subnets. So BDRs are the routers that would take over if the DR router went down or turned off for some reason. All of the routers, if there were more here, all the other ones would just be labeled DR other. So next hops are calculated by various metrics, such as bandwidth, which is how much data can be transmitted over a connection in a given amount of time, as well as how much delay there is between each link, the distance between each link, and how reliable each link is. These metrics are used to come up with a cost for each link. So based on a data's destination, the link with the lowest cost is the chosen path for the data. In this example, the DR router is the lowest cost. So the DR router would be the next hop. So using the OSPF neighbor table above, we can see that the interface our designated router is connected to is G00. And in the CDP neighbor table, we can see that G00 here is assigned to a router called ISP router 01, meaning that this ISP router 01 is our designated router. And it's easier to tell because we have 1.1.1 representing router 01. But if you didn't know, this would be a way to find out. You would just match the interface here in the CDP neighbor table to the local interface on the CDP neighbor table. So the CDP neighbor table also tells us which router interface our router is connected to on the other router. And that's this right here. So router 01 is connected to us on G00, and we're connected to router 01 on router 01's G0/1. By checking the router OSPF configuration here, we can see that router OSPF1 with the router ID 1.1.1, so this is our designated router, is advertising these routes here. Now let's take a closer look at EBGP. We have AS01 on one side with 3 interfaces: G00, G01, and FA0/2/0. So this one here, FA0/2/0 means fast Ethernet 0 with a virtual second sub interface on top of the physical interface. Hence the 2 here in the middle, right? And the first logical interface, hence the last 0. And each of these interfaces have to have an IP address if they're being used. And then on the other side here, we have AS32934 with interfaces 00, 01, and FA0/2/0 as well. So let's look at the BGP configuration of AS701, this router here that we're looking at. At the top, we have the command that tells BGP that the AS is 701 for the router. Here, we're telling the BGP that the neighbor router is in AS32934. And you can see that the IP we're giving is the IP of the neighbor router's interface we're connected to, right? So that's this here. Next, we have the 2 networks our routers want to advertise to our BGP neighbor. This will let our neighbor router know that it can get to these 2 networks through our router. And you can see that these 2 interfaces are in that network. Here we can see the BGP table on our router. So notice that the 2 networks at the top are the ones we're directly connected to, which is why the next hop is 0.0.0, right? The next 2 networks are the ones being advertised to us by our neighbor, which is why you see our neighbor as the next hop address. See, G00 on our neighbor is the next hop. Here's a look at the router BGP information on the AS32934 router. Notice that the BGP number is the AS number, and that the neighbor IP is the IP of the interface on our router that this Facebook router is connected to. And then here, we're looking at the BGP table for this Facebook router. And the BGP table shows that the 2 networks that are our router advertised to this Facebook router, right? So we were advertising these up here, and now they're shown up here. And here you can also see that the ones that are directly connected to this Facebook router has the 0.0.0 next hop because it's directly connected. And then here you can see that the next hop for the ones that we're advertising to Facebook is our interface that Facebook is connected to right here. And then you can see here that the next hop, which is us, shows that the AS number is 701, right? So that shows up right there. And the Facebook router's IP routing table also shows the BGP routes we advertise to it. The B next to the routes lets you know that BGP is how these routes are entered into the table. Once we get to the web server, we're only going to deal with the top application layers of the OSI model. Since we're receiving data, we're going to make our way up the OSI layers from 4 to 7. At the transport layer, the data will be reassembled from its various TCP segments. At the session layer, the web application will receive the session cookie ID, so the web server knows which logged in user is requesting the website data. At the presentation layer, the data will be reformatted by going through a decryption and decompression process. At the application layer, the web server's application on port 443 will see the request for the website's data and prepare a PDU of its own to send the data back to us. Let's take a look at the web server's application layer as it prepares a response to our data request. So the web server will send a PDU response with the requested web page data. Let's break this PDU down. At the top, we have the HTTPS protocol data header, so our laptop web browser application will know how to read the data. Then we have the body portion of the data, which is the user data of the web server. Here we see HTTP code 200, which means that the request was okay and that it will send the data back to the user. If the web page didn't exist, we'd get the 404 error code. The destination port is the ID assigned to our laptop's browser tab, which is a port that sent the data request to this web server. Finally, we have the source port of the web server, which is the port designated to this web server for sending and receiving HTTPS data, which is 443.